This week in Environmental Science, we'll be looking at Chapter 12, Freshwater, Oceans and Coasts. Here's our objectives for the chapter. We'll be understanding water's importance to people and ecosystems, aquatic systems, use of aquatic systems, water supply problems and solutions, water pollution, water quality legislation, wastewater treatment, ocean fisheries, and marine protected areas. Our central case study for the chapter is Starving the Louisiana Coast of Sediment. Louisiana's millions of acres of coastal wetlands were created over the past 7,000 years as the Mississippi River fanned out and deposited its sediments at its delta before emptying into the Gulf of Mexico. The Mississippi River accumulates large quantities of sediment from water flowing over land and into streams. Much of this sediment originates from the Missouri River basin, which drains America's agricultural heartland. Louisiana's vital coastal wetlands have a job to do. They support biodiversity and they protect the coast from storms, often acting as a windbreak from the strong winds. The Mississippi River sediments help to keep soil levels high and water stable and plants healthy. But unfortunately, the wetlands are shrinking over time. In fact, Louisiana loses 65 kilometers squared or 25 miles squared of coastal wetlands each year. That's about the size of Manhattan Island in New York City. Comparison of wetland area from the mid-1800s to the early 1990s show a drastic decrease in wetlands around this area, about the size of roughly Delaware. They're shrinking because people have changed the Mississippi River by putting up dams and levees. These items stop sedimentation and they prevent water from spreading into the delta like it should. And the pictures over to the side here, you can see this big impact of human use of the Mississippi River and what that has done to the area here in Louisiana, and how the coast down here is actually disappearing. Oil and gas extraction promote wetland losses. The withdrawal compacts land and it lowers soil levels, and building canals for better transportation in the area fragments wetlands and increases erosion. And oil spills, when those happen, they destroy vegetation and other wildlife. Diverting the Mississippi River is one of the solutions that have been proposed. It's thought that by diverting the Mississippi River into coastal wetlands instead of shooting it out into the Gulf in the river's main channel would be a big help. Proponents of this approach point to a nearby river which currently diverts 1/3 of the lower Mississippi River's volume and carries it to the Gulf. The Restore Act, RESTORE, has helped to bolster efforts in this area. This money is available from legislation passed in the aftermath of the Deepwater Horizon spill. The act creates a comprehensive ecosystem restoration plan for the Gulf Coast, financed by 80% of the fines paid for Clean Water Act violations associated with the spill. Given the conflicting demands we put on waterways for water withdrawal, shipping, and flood control, there's no easy solutions. But how we tackle problems like these in the Louisiana coastal wetlands will help determine the long-term sustainability of one of our most precious natural resources, the aquatic ecosystems that provide us life-sustaining water. Water may seem abundant, but drinkable water is actually rare. Fresh water actually makes up only about 2.5% of all of our water. About 97.5% of the Earth's water resides in oceans, and it's too salty to drink or to use on our water crops. Of this fresh water, that 2.5%, it's mostly tied up in glaciers and ice caps and aquifers. Fresh water is defined as water that's relatively pure with few dissolved salts. Water is renewed and recycled by the water cycle. Precipitation forms our rivers, which carry water to oceans and then to lakes. And rivers interact with ponds, wetlands, and coastal systems. And then groundwater exchanges water with surface sources. And the water cycle creates a web of interconnected aquatic systems. It exchanges water, organisms, sediment, and pollutants. And what happens in one system, though, affects other systems. Groundwater is 1/5 of all fresh water. Or we could say about 20% of Earth's supply of fresh water. Groundwater is the water beneath the surface held in pores in soil and rock. Aquifers are the porous formations of rock, sand, or gravel that actually hold water. There's a zone of aeration, and this is the pore spaces that are partly filled with water. And then there's the zone of saturation, and these are the spaces that are filled with water. The water table is the boundary between these two zones. The largest known aquifer is the Ogallala Aquifer, which underlies the Great Plains of the United States. Water from this massive aquifer has enabled American farmers to create the most productive grain-producing region in the world. However, unsustainable water withdrawals are threatening the long-term use of this aquifer for agriculture. Here's a diagram on this slide showing us the parts of these underground aquifers. Groundwater may occur in unconfined aquifers, above impermeable layers, or in confined aquifers under pressure between impermeable layers. Surface water is the water on Earth's surface and comprises 1% of all fresh water. It's vital for our survival and ecological systems and becomes groundwater by infiltration down into the soil. Runoff is water that flows over land. Water merges in rivers and then ends up in a lake or in the ocean. A tributary is a smaller river flowing into a larger one. The watershed is the area of land drained by a river and its tributaries. Rivers can shift course over time. They shape the landscape through which they run and can carve out valleys as they change course, and damming can reduce this river meandering. In fact, we can look at here in southern Minnesota how rivers have shaped our landscape ever since the glaciers melted around 10,000 years ago or so. We can travel into some of our big river valleys that were carved during that melting time, such as in Mankato down into the Minnesota River. A floodplain is the areas nearest to the river's course that are flooded periodically, and the soils are usually fertile as a result of this flooding. As a river floods, it deposits nice, rich, fertile soil over the landscape. These are good areas for agriculture. Lakes and ponds are ecologically diverse systems. Lakes and ponds are bodies of standing surface water and have several zones, including the littoral zone that we can see on the diagram to the right. This is the nutrient-rich edge of a water body. It's characterized by rooted aquatic plants that grow in this very shallow part. There's the benthic zone here on the bottom. It extends along the bottom of the water body and is home to many invertebrates. Those are animals without backbones. Then there's the limnetic zone right here. It's the open portion of the lake or pond where sunlight can actually penetrate. So this allows organisms that can do photosynthesis to do so. Open water below this zone, where light does not penetrate, has no photosynthesis, and therefore would support fewer organisms because there's less oxygen available, because oxygen is one of the products of photosynthesis. Oligotrophic lakes and ponds are characterized by low nutrient and high oxygen conditions, but they can transform into other types of lakes, including eutrophic lakes and ponds, which have high nutrient and low oxygen conditions. Eventually, water bodies can actually fill in through the process of aquatic succession over many, many, many years. This is actually happening in southern Minnesota in many places where there used to be many wetlands that were left over from our glaciated stage when those glaciers melted. Eutrophication can also result from human-caused nutrient pollution. That's when items like nitrogen and phosphorus from fertilizers run off into our streams and lakes and ponds. Because there's so many nutrients, then we get too much algae growth. Freshwater wetlands include marshes, swamps, bogs, and vernal pools. In wetlands, the soil is saturated with shallow standing water. And these can be classified into freshwater marshes, which are shallow, where plants grow above the surface, swamps, which is shallow water in forested areas, and bogs, which are ponds covered in thick, floating mats of vegetation. Vernal pools are adapted to seasonal drying. These are seasonal wetlands that form in the early spring from rain and snowmelt and dry up once the weather becomes warmer. Wetlands are extremely valuable for wildlife, and they provide important ecosystem services, such as slowing the runoff of water, reducing flooding. They recharge our aquifers, and they filter out pollutants for us. But unfortunately, people have drained wetlands, mostly for agriculture. People divert and withdraw water, and they channelize rivers and build dams, which has had a negative impact on our wetlands. And so, the U.S. has lost over half of all its wetlands. The oceans are an important component of Earth's interconnected aquatic systems. The vast majority of rivers empty into oceans. So the oceans receive most of the inputs of water, sediments, pollutants, and organisms carried by freshwater systems. The oceans influence virtually every environmental system and every human endeavor. So even if you live in landlocked regions far from the coast, the oceans affect you and you affect the oceans. Oceans cover about 71% of Earth and hold 97% of our surface water. Ocean water is 96.5% water plus dissolved salts. Surface water is warmer than subsurface water because it's warmed by the sun and less dense. And deeper water is dense and sluggish because it's unaffected by wind, storms, sunlight, and temperature. Ocean water travels in currents, which are vast river-like flows in the upper 1,300 feet of the ocean. They're driven by wind, heating and cooling, gravity, density differences, and the Coriolis effect. The Coriolis effect is the deflection that's caused by our curving global wind patterns. And we'll study that in one of our future chapters. Upwelling is the rising of deep, cold, dense water toward the surface. Because water is rich in nutrients from the bottom, upwellings often support high primary productivity and lucrative fisheries, such as those along the coasts of Peru and Chile. At downwellings, warm surface water, rich in dissolved gases, is displaced downward, providing an influx of oxygen for deep water life and burying carbon dioxide in ocean sediments. Many parts of the ocean floor are rugged and complex and can include underwater volcanoes, steep canyons, and deep trenches. And in fact, the planet's longest mountain range is underwater. It's the Mid-Atlantic Ridge. It runs the length of the Atlantic Ocean. Here's a diagram showing our rugged ocean floor. Movement of ocean water affects global climate. The horizontal and vertical movements of ocean water can have far-reaching effects on climate globally and regionally. The thermohaline circulation is a worldwide current system in which warmer, fresher water moves along the surface and colder, saltier water, which is denser, moves deep beneath the surface. One segment of this worldwide conveyor belt system is the warm surface water in the Gulf Stream that flows across the Atlantic Ocean to Europe. As this water releases heat to the air, keeping Europe warmer than it would otherwise be, the water cools, becoming saltier through evaporation. It becomes denser and then sinks. This creates a region of downwelling known as the North Atlantic Deep Water, or the NADW. Scientists hypothesize that interrupting the thermohaline circulation could trigger rapid climate change. If global warming causes much of Greenland's ice sheet to melt, the resulting freshwater runoff into the North Atlantic would make surface waters less dense, because fresh water is less dense than salt water. This could stop the NADW formation and shut down the northward flow of warm water, causing Europe to cool rapidly. Some data suggests that the thermohaline circulation in this region is already slowing, but other researchers maintain that Greenland will not produce enough runoff to cause a shutdown this century. Another interaction between ocean currents and the atmosphere that influences climate is the El Niño Southern Oscillation, or the ENSO. This is a systematic shift in atmospheric pressure, sea surface temperature, and ocean circulation in the tropical Pacific Ocean. Under normal conditions, prevailing winds blow from east to west along the equator, from a region of high pressure in the eastern Pacific to one of low pressure in the western Pacific, forming a large-scale convective loop in the atmosphere. The winds push surface waters westward, causing water to pile up in the western Pacific. As a result, water near Indonesia can be 20 inches higher and 8 degrees Celsius warmer than water near South America. The westward moving surface waters allow cold water to rise up from the deep in a nutrient-rich upwelling along the coast of Peru and Ecuador. This can cause Peru and Ecuador to have rich fisheries there. El Niño conditions are triggered when air pressure decreases in the eastern Pacific and increases in the western Pacific, weakening the equatorial winds and allowing the warm water to flow eastward. This suppresses the upwelling on the America's Pacific coast, and it can devastate fisheries and cost billions of dollars. This phenomenon was called El Niño, which is Spanish for little boy, by Peruvian fishermen because of the arrival of warmer waters usually occurred shortly or after Christmas. Coastal industries like Peru's anchovy fisheries are devastated by these events. La Nina events are the opposite of El Nino events. In a La Nina event, cold waters rise to the surface and extend westward in the equatorial Pacific when winds blowing to the west strengthen and weather patterns are affected in opposite ways. ENSO cycles are periodic but irregular, occurring every 2 to 8 years or so. Scientists are trying to determine whether warming air and sea temperatures may be increasing the frequency and the strength of these cycles. With their variation in topography, temperature, salinity, nutrients, and sunlight, marine and coastal environments may feature a variety of ecosystems. These systems may not give us the water we need for drinking and growing crops, but they teem with biodiversity and provide many other necessary resources. 67% of all people live within 100 miles of the ocean. Estuaries are water bodies where rivers flow into the ocean, which then mixes fresh water with salt water. Shallow water nurtures plants that provide critical habitat for shorebirds and shellfish. Estuaries are affected by development, pollution, habitat alteration, and overfishing. Salt marshes occur along coasts at temperate latitudes. They have tides that wash over gently sloping, sandy, and silty substrates, and tidal creeks, which are channels that tides flow into and out of daily. They have salt-tolerant plants and also filter pollution and stabilize shorelines as an ecosystem service. They have high primary productivity and provide critical habitat for birds and commercial fish and shellfish species. In tropical and subtropical latitudes, mangrove forests replace salt marshes along the coasts. Mangroves are salt tolerant and they have unique roots that curve upward like snorkels to attain oxygen and downward like stilts to support the tree in the changing water levels. They're characterized by a lot of fish, shellfish, crabs, snakes, and other organisms that thrive among the root networks. And birds feed and nest in the dense foliage of these coastal forests. Mangroves protect shorelines from storm surges. They filter pollutants and capture eroded soils, protecting offshore coral reefs. They also provide materials that people have used for food and medicine and tools. 50% of mangroves have been destroyed for resorts or for shrimp farms. Where the ocean meets the land, intertidal or littoral ecosystems spread between the uppermost reach of the high tide and the lowest limit of the low tide. Tides are the periodic rising and falling of the ocean's height due to the gravitational pull of the moon and the sun. Organisms spend part of their time submerged in water and part of their time exposed to the sun and the wind. Life abounds along these rocky shorelines because environmental conditions can change quite dramatically. Here's a diagram showing some of the variety of life that can be among these crevices of these rocky shores, including sea anemones, and coral, and crabs, and mollusks. Along many temperate coasts, large brown algae or kelp grow from the floor of continental shelves reaching up toward the sunlit surface. Some kelp can grow up to 200 feet tall, forming kelp forests. They provide shelter and food for organisms. They absorb wave energy and protect shorelines from erosion. Kelp even serves as food and as thickeners in cosmetics, paints, paper, and soaps for we humans. Coral reefs are treasure troves of biodiversity. A coral reef is a mass of calcium carbonate composed of the skeletons of millions of tiny invertebrate corals that have built up over thousands of years. They protect shorelines by absorbing waves. Corals are tiny organisms that live in shallow subtropical or tropical waters. They're related to organisms like sea anemones and jellyfish. In fact, they're in their same phylum called Cnidaria. And these organisms use their tentacles to catch food. And they derive nourishment from other symbiotic algae as well. Coral reefs are a valuable ecotourism destination because of its formations and its biodiversity. Unfortunately, corals are experiencing alarming declines. Eutrophication, which is the nutrients that go into their areas by runoff, promotes the algal growth there and smothers corals. In coral bleaching, the zooxanthellae die and leave corals, depriving them of their nutrition. That's the organism they have a symbiosis with. This results from warmer water, from climate change, from pollution and eutrophication. Ocean acidification is when oceans absorb excess carbon dioxide, which then lowers the pH of the seawater and reduces carbonate ions and dissolves calcium carbonate from the coral shells. This is also having a negative impact on coral reefs. Some ocean regions support more life than others. The photic zone is the well-lit top layer that supports high primary productivity, characterized by warm, shallow waters of continental shelves, and are the most productive and support the highest biodiversity of life. The pelagic zone is the habitats and the ecosystems occurring between the ocean surface and the floor. And the benthic zone is the habitats and the ecosystems occurring on the ocean floor. Surface primary production and animal populations are high around the nutrient upwellings. They include many organisms from phytoplankton to the larger whales. Predators include larger fish, sea turtles, and sharks. Animals in the deep water must tolerate high pressure and the dark. They scavenge carcasses and detritus and are predators, or they get food from mutualistic bacteria as well. Tube worms and others get energy from chemicals that are emitted by the hydrothermal vents down there. There's a lot of effects of human activities on waterways. Remember, water is a limited but renewable resources as long as we use it sustainably. People are withdrawing water at unsustainable rates. Surface and groundwater are being depleted, and 1/3 of the world's people are affected by these shortages. People also engineer waterways by building dams and levees and diversion canals for things like supplies and transportation and flood control. And then what we do in one part of the aquatic system affects other parts. Freshwater and human populations are unevenly distributed across the earth. Water is unevenly distributed in space and time. Different areas possess different amounts of water. People are not distributed according to fresh water. Climate change will worsen water conditions. Change precipitation patterns can have a big effect. The melting of glaciers and droughts and floods. 70% of our water use is actually for agriculture, for crop irrigation and the watering of livestock. 20% goes to industry and 10% for residential use. Consumptive use is the water removed from an aquifer or surface water body, and that's not returned. For example, irrigation. Non-consumptive uses does not remove or only temporarily removes water, such as for electricity generation at hydroelectric dams. In many places, we're withdrawing water at unsustainable rates. In major rivers like the Colorado, they run dry before reaching the sea. Reduced flow has devastating consequences and drastically changes the river's ecology and plant community and destroys fish and invertebrates. Here's an example. The Aral Sea in Central Asia was once the world's fourth largest lake. However, it's been shrinking because so much water was withdrawn to irrigate cotton crops, and ships were stranded along the former shoreline of the Aral Sea because the waters receded so far and so quickly. Today, restoration efforts are beginning to reverse the decline in the northern portion of the sea, and the waters there are slowly rising. Irrigation for agriculture is the main contributor to unsustainable water use. Worldwide, roughly 15 to 35% of water withdrawals for irrigation are thought to be unsustainable. In areas where agriculture is demanding more fresh water than can be sustainably supplied, water mining or withdrawing water faster than it can be replenished is taking place. In these areas, aquifers are depleted or surface water is being piped in from other regions to meet demand for irrigation. Groundwater can be depleted. In fact, it's easily depleted. Aquifers recharge slowly over time, and we're mining aquifers. Remember, water mining is removing water faster than what we put back. As aquifers are mined, water tables drop and freshwater wetlands dry up. Water becomes harder and more expensive to get. Salt water intrudes into the coastal aquifers, and compactive soil loses its porosity, making recharge even harder yet, making the problem worse. In parts of Mexico, India, and China, and some Asian and Middle Eastern nations, water tables are falling 1 to 3 meters per year. In the United States, overpumping has drawn the Ogallala Aquifer down by more than 320 million liters. That's 85 trillion gallons. That's a volume equal to half the annual flow of the Mississippi River. As aquifers lose water, they become less able to support the overlying strata and soil. That's the land surface above. And they can sink. This causes a sinkhole. These days, our groundwater is being withdrawn for a new purpose, to be packaged in plastic bottles and sold on supermarket shelves. For bottled water, an average American drinks 30 gallons per year of this. People drink bottled water for portability and convenience, and they think it tastes better, or they have this thought that it's healthier. This may or may not be the case. Bottled water is actually no better than tap water, and the energy costs for bottling it are 1,000 to 2,000 times more than that of tap water. Remember, you have to pay for manufacturing of the bottle and transporting this product. 75% of the bottles are then thrown away and not recycled. That's 30 to 40 billion a year. Flooding. It's a normal natural process in which water spills over a river's banks and can deposit some nutrient-rich sediments over large areas. Dikes and levees, those are long raised mounds of earth along the banks of the rivers, hold water in the channels, and they make floods worse by forcing water to stay in the channels, which then can overflow. We've erected thousands of dams. A dam is any obstruction placed in a river or stream to block the flow. They're erected to prevent floods and provide drinking water and allow irrigation and even to generate electricity. Worldwide, we've erected more than 45,000 large dams. We've also built tens of thousands of smaller dams. Only a few major rivers in the world remain free-flowing. Those undammed rivers run through the tundra and taiga of the Arctic and in remote areas of Latin America and Africa. A reservoir is an artificial lake created by a dam, and it's there to store water for human use. Dams produce a mix of benefits and costs. As an example, let's consider the world's largest dam, the Three Gorges Dam on China's Yangtze River, completed in 2008. Its reservoir stretches 385 miles. This dam will help control the large floods that have historically occurred on the banks of the Yangtze. It'll also facilitate shipping, and it'll generate enough hydroelectric power to replace dozens of large coal or nuclear plants. However, the Three Gorges Dam costs $39 billion to build, and its reservoir displaced 1.24 million people and submerged productive farmlands, wildlife habitat, and 10,000-year-old archaeological sites. Tidal marshes at the Yangtze's mouth are eroding away and deprived of the sediments that now settle in the dam's reservoir as the river slows. Many scientists also worry that the Yangtze's many pollutants will be trapped in the reservoir, making that water undrinkable. People who feel that the costs of some dams outweigh their benefits are pushing for such dams to be dismantled. By removing dams and letting rivers flow free, they say that we can restore ecosystems and reestablish economically valuable fisheries and revive river recreation, such as fly fishing and rafting. But as we build dams, we need to remember that they age and need repair. Old dams, or those that are no longer economical, are candidates for removable, and we've removed 400 of them in the United States, and as licenses come due, 500 more may be removed. And all of this costs money. As humans, we divert surface water for our needs. People have long diverted water from rivers and lakes to farms, homes, and cities. For instance, the Colorado River was piped to supply the city of Denver early in its course. The world's largest diversion project is in China. The goal is to move water from the water-rich northern China to drier farms and cities in southern China. This has taken 3 sets of massive aqueducts, over 1,500 miles long, and are being built. Critics say not enough water can be moved. The project will cause huge environmental damage and will displace hundreds of thousands of people. Solutions. We can either increase supply or reduce demand. Dams have increased supplies, but most major rivers have already been dammed. Desalination or desalinization is the removal of salt from seawater. That could be a solution. There's 20,000 facilities operating worldwide. Drawbacks are that it's very expensive and it requires large inputs of fossil fuel energy to do this. It kills aquatic life at water intakes and generates concentrated salty waste. It's mostly found in wealthy oil-rich nations where water is extremely scarce. Reducing demand is harder politically. It involves changing our behaviors as humans, but offers better economic returns and causes less ecological and social damage. Reducing demand is already paying off. From 1980 to 2005, the U.S. population grew 31%, but water consumption actually decreased by 5%. Agricultural demand can be reduced. Most water is used in agriculture. Flood and furrow method floods fields, but plants use only 40% of the water applied. As much of the water evaporates or seeps into the ground far away from the crops. Therefore, we need to find more efficient irrigation methods. Other methods that are more efficient include low pressure spray irrigation that squirts water downward toward the plants, and drip irrigation systems that target individual plants and introduce water directly onto the soil. Experts estimate that drip irrigation, in which as little as 10% of the water is wasted, could cut water use in half while raising crop yields. This technology could produce as much as $3 billion in extra annual income for farmers of the developing world. Researchers are currently experimenting with various methods and approaches to develop reliable, inexpensive drip irrigation systems. Another way to reduce agricultural water would be to eliminate government subsidies for the irrigation of crops that require a great deal of water, such as cotton and rice, in arid areas. Therefore, we would match crops to the land and climate better. We could also use selective breeding and genetic modification to produce crops that require less water. In our residences, we can reduce water use by installing low-flow faucets, shower heads, washing machines, and toilets. High-efficiency toilets and shower heads provide the biggest savings because these are typically the two largest indoor uses of water. We can reduce outdoor water use by catching and storing rain runoff in a barrel and replacing exotic vegetation with native plants adapted to our region's natural precipitation patterns. For example, more and more residents in the U.S. Southwest are practicing xeriscaping, which is a type of landscaping that uses plants adapted to arid conditions. Industry and municipalities can shift to processes that use less water. They can recycle wastewater for irrigation and industrial uses. They can fix leaky pipes and retrofit homes with better plumbing. They can audit industries and promote conservation. Nations often cooperate to resolve water disputes. Population growth, expansion of irrigated agriculture, and industrial development doubled our annual freshwater use between 1960 and 2000. These increased withdrawals of fresh water can lead to shortages, which then can lead to conflict. Many security analysts predict that the water's role in regional conflicts will increase as human population grows and as climate change alters precipitation patterns. A total of 261 major rivers cross national borders, and trans-boundary disagreements are common. Access to water is already a key element in the disagreements among Israel, the Palestinian people, and neighboring nations in the arid Middle East. Yet, on the positive side, many nations have cooperated to resolve water disputes. India has struck agreements to co-manage trans-boundary rivers with Pakistan, Bangladesh, Bhutan, and Nepal. In Europe, nations along the Rhine and the Danube rivers have signed water-sharing treaties. Such progress gives reason to hope that water wars will be few and far between in the coming decades. Here's a map showing some of these trans-boundary water areas. Water pollution and its control. We have seen that people affect aquatic systems by withdrawing too much water and by erecting dams, diversions, and levees that alter the system's natural processes. Introducing toxic substances and disease-causing organisms into surface waters and groundwater is yet another way that people adversely affect aquatic ecosystems and even threaten human health. Developing nations have actually moved toward cleaning up water pollution, but still, half of the world's major rivers are seriously depleted and polluted. Surrounding ecosystems are being poisoned, and people's health and livelihood are being threatened. The invisible pollution of groundwater is called a covert crisis. Pollution is the release of matter or energy that causes undesirable impacts on health and well-being of humans and other organisms. Water pollution has many forms and can cause diverse impacts on aquatic ecosystems and human health. There's chemical indicators like pH, nutrient concentrations, and dissolved oxygen concentrations. There's physical indicators like temperature, turbidity, which is the density of suspended particles in water, and biological indicators, such as the presence of harmful microorganisms and the measurement of species diversity. All of these can help to measure water pollution. A point source is a discrete location of water pollution, such as a factory or a sewer pipe or an oil tanker. This is addressed by the U.S. Clean Water Act. They've had some success by targeting industrial discharges. Non-point sources of pollution are multiple inputs of pollution over larger areas, such as farms and city streets and neighborhoods. This could actually be a greater threat to water quality because it comes from so many different places and it's harder to minimize it. Pesticides, petroleum products, synthetic chemicals, these are all toxic. Toxic metals, arsenic, lead and mercury, acid rain, and acid drainage from mines can contribute to pollution. The effects include poisoning of animals and plants and alteration of aquatic ecosystems and human health problems. There are some solutions, such as to issue and enforce more stringent regulations of industry, or to modify industrial processes and modify our purchasing decisions. Pathogens can enter water through inadequately treated sewage and animal waste from feedlots. Biological pollution causes more health problems than any other type of water pollution. 1 billion people don't have safe water. 2.6 billion don't have adequate sewer or sanitation facilities. Solutions? Well, disinfecting drinking water and treating wastewater. Public education to encourage personal hygiene, and government regulations protecting food. There can also be nutrient pollution from fertilizers and farms, sewage, lawns, golf courses. Remember, these can all lead to eutrophication and hypoxia of the organisms living in the area that's affected. Excess nitrogen and phosphorus in water boosts algal growth, and the spreading algae then covers the surface. That then decreases the sunlight, and organisms then die. Bacteria eat these dead organisms, which then reduces dissolved oxygen, which can kill other organisms like fish and shellfish. It's a cascading effect. Solutions include treating wastewater, reducing fertilizer application, such as not fertilizing our lawns, and using phosphate-free detergents. We can also plant vegetation to decrease nutrient flow into water. Human activities dramatically increase the rate at which eutrophication occurs. Red tides or harmful algal blooms can occur. This is when excessive nutrients increase marine algae, which releases powerful toxins and can kill organisms and even people, and then has the effect of decreasing tourism and fishing. Biodegradable materials can decrease dissolved oxygen in water. Human waste, animal manure, paper pulp, yard waste, and grass clippings and leaves are all biodegradable materials. When these enter water, they can decrease the dissolved oxygen when organisms have to break them down. Wastewater is when humans release biodegradable wastes from their toilets and showers, from stormwater runoff, etc. Developed nations treat their wastewater, and many developing nations don't treat it. Sediment can also lead to pollution. Sediment in rivers can impair aquatic systems. Clear cutting, mining, and clearing land for housing and cultivating farm fields exposes soil to erosion, which increases then the runoff of sediments. It dramatically changes aquatic habitats. It impairs organism respiration. Fish may not be able to survive it. And the cloudy water can block the sun and decrease photosynthesis. Solutions? Well, we can adopt sustainable soil practices. We can avoid large-scale disturbance of vegetation, and we can maintain riparian vegetation to trap sediments. The riparian zone is the zone of vegetation near a body of water. It can act as a buffer. Oil pollution is another problem. Large spills are infrequent but can be very, very devastating. There can also be natural seepage and boat leakage and runoff from roads and parking lots. There can also be spills during transports and leakage during extraction. In 1989, the oil tanker Exxon Valdez ran aground and polluted the Prince William Sound along the Alaskan coast. The dangers of oil pollution made headlines once again in 2010 when the British Petroleum's Deepwater Horizon offshore drilling platform exploded and sank into the Gulf of Mexico off the Louisiana coast. Oil gushed from the platform's underwater well and spread widely by ocean currents and washed up on coastal areas across the northern Gulf of Mexico. The economic and ecological impacts of the spill were visited on hundreds of miles of water, sediments, and shoreline along the coasts of Louisiana, Mississippi, Alabama, and Florida. Even organisms in the deep water were affected. A 2012 study found that corals living 11 kilometers from the oil well at a depth of 4,495 feet were adversely affected by the exposure to the underground or underwater plume of oil emanating from the spill site. Given the severity of the Deepwater Horizon and other oil spills, it may be surprising to learn that about half of the petroleum entering the world's oceans in a given year originate from natural seeps in the ocean bottom. The impact on organisms from these petroleum releases are less severe than the spills, however, because the seepage from the ocean floor is more diffuse and limited to a smaller area. Much of the oil entering the ocean from sources other than seeps accumulates in waters from innumerable, widely spread, small non-point sources, like shipping vessels, recreational boats that leak, and motor oil from vehicles. Oil spills have decreased as a result of an emphasis on spill prevention and response. The U.S. Oil Pollution Act of 1990 provided $1 billion in prevention and a cleanup fund. That all ships must have double hulls by 2015, and that's this year. Nets and plastic debris can also be a problem. Plastic items dumped into the sea harm and kill wildlife. Examples include fishing nets, plastic bags and bottles, fishing line, buckets, and floats. Mammals, seabirds, and sea turtles could eat the plastic or get caught up in it and die. Plastic trash is accumulating in gyres, which are ocean regions where currents converge. One such area is the Great Pacific Garbage Patch in the northern Pacific, an area larger than Texas, in which tiny pieces of floating plastic outnumber organisms by a 6-to-1 margin. We need to remember that plastics take 500 to thousands of years to degrade at sea, and there's no viable way right now to collect all the innumerable bits of plastic that litters the oceans. Such efforts were aided by the Marine Debris Research Prevention and Reduction Act, passed by Congress in 2006. Its goal is to minimize this harm by reducing, reusing, and recycling plastic. Heat can also be a pollution called thermal pollution. Water that's too warm causes problems too. It holds less oxygen. Cooling an industrial facility with water heats the water, and then when it's released, it heats the river. Removing streamside cover raises water temperature as well. Water that's too cold can also cause problems. Water at the bottom of reservoirs behind dams is colder. When water is released downstream, water temperatures drop suddenly and can kill aquatic organisms. Water pollutants can contaminate groundwater. Groundwater pollution is hard to detect and address. Groundwater retains contaminants for decades and longer. Contaminates break down more slowly because of lower levels of sunlight and microbes and dissolved oxygen. Some toxic chemicals can occur naturally in these areas, such as aluminum, fluoride, and sulfates. And pollution from human activities leaches through the soils into the groundwater. Agricultural nitrates cause blue baby syndrome. This is caused by the leaking of underground storage tanks that are improperly designed and the improper storage of hazardous wastes. Nitrate in drinking water from our fertilizers has been linked to cancers and miscarriages, and again what's called this blue baby syndrome, which is a condition in which the oxygen carrying capacity of infants' blood is reduced. Legislation and regulation have helped to reduce water pollution. Water pollution was actually worse decades ago, but U.S. citizen activism and government response has resulted in legislation during the 1960s and 1970s, such as the Federal Water Pollution Control Act of 1972, which was then renamed as the Clean Water Act in 1977. It made it illegal to discharge pollution without a permit and set standards for industrial wastewater. It's funded building of sewage treatment plants as well. So the situation is much better now, and we can see some of the progress by our Great Lakes, which are much cleaner, but they still have issues as well. This enforcement of water quality, though, needs money. Conditions improve when citizens push their government to take action. Underfunded and understaffed state and federal regulatory agencies cannot investigate violations very well. And so violations of the Clean Water Act have risen. 10% of Americans are now exposed to unsafe drinking water. The new EPA administrator has promised improvement. We treat our drinking water. Treatment of drinking water is widespread and successful in developed nations. Before water reaches the user, it's chemically treated and then filtered and then disinfected. The EPA sets standards for over 90 drinking water contaminants. Local governments and private water suppliers must meet these standards. Water treatment has reduced deaths from diseases, and it's one of our greatest advances of modern times. Prior to the passage of the Clean Water Act, cities and towns regularly released untreated sewage into waterways. This led to oxygen depletion, contamination, pollution. Wastewater treatment is now a mainstream practice in rural areas. Septic systems are the most popular method of treating wastewater. In a septic system, wastewater runs from the house to an underground septic tank, inside which solids and oils separate from water. The clarified water proceeds downhill to a drain field of perforated pipes laid horizontally in gravel-filled trenches underground. Microbes decompose pollutants in the wastewater that these pipes emit. Periodically, solid waste from the septic tank is pumped out and taken to a landfill. Municipal sewer systems, areas that are populated, municipal sewer systems carry wastewater to wastewater treatment plants. At the plant, incoming wastewater is first passed through screens to capture large objects, and then it's sent to primary treatment, where about 60% of the suspended solids in the wastewater settle out when the wastewater is allowed to sit in settling tanks. Wastewater then proceeds to secondary treatment, in which the water is stirred and aerated so that aerobic bacteria consume most of the small particles of the organic matter that remain in the wastewater. Roughly 90% of the suspended solids may be removed after secondary treatment. Finally, the clarified water is treated with chlorine or sometimes a UV light to kill bacteria. The treated water, which is called wastewater effluent, is then typically released into a river or the ocean. In some cases, effluent is reclaimed and used for watering lawns and golf courses, for irrigation, or for industry. Here's a diagram of a typical wastewater treatment facility. Wastewater initially passes through screens again to remove the large debris and the grit, and then it enters tanks called the primary clarifiers, in which the solids settle to the bottom and the oils and greases float to the top for removal. Clarified water then proceeds to aeration basins that oxygenate the water to encourage the decomposition by aerobic bacteria. Water then passes into secondary clarifier tanks for removal of further solids and oils. Next, the water can be purified by chemical treatment like chlorine, and carbon filters, and exposure to UV light. And the treated water, called effluent, then can be piped into natural water bodies or used for urban irrigation or for farms. Sludge is the solid material resulting from the treatment. It's decomposed microbially and then landfilled, incinerated, or used as fertilizer. Microbes polish the treated wastewater and remove plant nutrients. The cleansed water is released into waterways and percolates underground. The U.S. has over 500 artificial or restored wetlands. Releasing wastewater effluent can help restore marshes. Nutrients can increase marsh grass growth, and increased organic matter offsets natural soil compaction. So these wetlands can aid wastewater treatment. Again, showing the importance of wetlands. Emptying the oceans. We affect the oceans and their biological resources by engineering waterways with dams and levees, and by introducing water pollutants directly into the ocean or rivers that empty to the sea. In addition, we're putting pressure on oceans by over-harvesting marine fish species. This threatens the balance and functioning of marine and coastal ecosystems. Half of the world's marine fish populations are fully exploited. 28% of fish populations are overexploited and heading to extinction. With current trends, populations of all ocean species we fish for will collapse by 2048. The total global fisheries catch has stalled. Total fisheries catch leveled off after 1998, despite increased fishing effort. Many fear a global decline in fisheries is imminent if conservation measures are not taken. And fishing has industrialized. How can the fisheries catch seem to be stable when fisheries are collapsing? Well, fleets are fishing in increasingly remote areas, and they're engaging in more intensive fishing, and they're capturing smaller fish than before, and they're capturing less desirable species. Today's industrialized fishing fleets are huge vessels that use powerful technologies to capture fish in huge volumes. For instance, drift nets are transparent nylon nets that span large expanses of water to capture passing fish, shown in the picture here. Longline fishing uses extremely long lines with thousands of hooks, shown in the middle picture here. And bottom trawling entails dragging immense nets through the water or on the ocean floor, shown in the last picture here. Bycatch is the accidental capture of the non-target animals like sea turtles and dolphins and seals. It kills millions of animals each year. Longline fishing can kill turtles, sharks, and seabirds even. And bottom trawling is likened to clear cutting and strip mining and destroys complex communities like coral reefs. Modern fishing fleets deplete marine life rapidly, unfortunately. Oceans contain only 1/10 of the large-bodied animals that they once did. Overfishing has caused many fisheries to collapse and destroys the fishing economies. The groundfish stocks have collapsed, including cod, halibut, and flounder. Bans in the 1990s by the US and Canada have helped restore fisheries, but it's a slow path to recovery. Red snapper stocks have been overfished and depleted in the Gulf of Mexico, and current populations are only 3% of historic levels. Management was based on maximum sustained yield, the number of fish that can be harvested without reducing future catches. Despite management, stocks have plummeted, and it's time to rethink fisheries management. We need ecosystem-based management and to shift the focus away from species and toward the larger ecosystem. And protecting oceans areas can help species recover. Marine protected areas, or MPAs, are established along the coastlines of developed countries and still allow fishing or other extractive activities. Marine reserves are areas where fishing is prohibited altogether. It leaves the ecosystems intact without human interference. It improves fisheries and the young fish disperse into surrounding areas. Many commercial and recreation fisheries do not support reserves, but reserves work. Species density, biomass, size, and diversity have all increased 1 to 2 years after establishment. In conclusion, expanding population and increasing water usage are straining water supplies, and they're affecting surface waters and groundwater. Water pollution harms health and ecosystem stability. Overharvesting threatens the ocean's biodiversity. Efficiency can reduce the demand for water. Better regulation and concern have improved water quality, and marine reserves give hope for ecosystem restoration and the future of fisheries.